All right, we're just going to pick up where we left off last week. Here's another example of an integral where we would probably want to use a substitution of some sort because we've got a composition going on here. So I'm going to let u represent the inside function, which would be the 5x. And if that's the case, then du would equal 5 dx. Now I don't need anything in this case except for the dx, right? Because when I integrate this thing, an e to the x function's derivative is itself. So what I need, because there's nothing else outside of this function, is I just need the dx. So what do I need to replace that dx with? Well, if I divide by 5 on both sides, it's going to be a 1/5 du. Okay, so when I have the integral e to the 5th, or 5x dx, I'm going to replace that with a 1/5, and I'll write it like this first, I suppose, e to the u du. And where these components are coming from, right, is 5x is u, and dx is 1/5 du. So that's what I've replaced each of these two components with. All right, so I can move that constant out, 1/5 times the integral of e to the u du, and now I can take the antiderivative here, right? Because if I take the antiderivative of e to some power, that's just going to be e to that same power. Don't forget there could be some sort of constant, all right, plus c, and so when I distribute that 1/5, that leaves me with a 1/5 e to the u plus c. And again, in the last video, we talked about why I don't need that 1/5 to be distributed to the c. So that would be our final answer there. All right, next example. We've got a composition here, and we've got a lot going on. We've got the square root of a function. So just based on the pattern that we've been following so far, it'd probably be a good idea to let u equal 1 plus x squared. And if that's the case, then du is going to equal 2x dx. All right, so what are we going to need here? Well, that's sort of tricky because there is going to be something that's unaccounted for in this case. I can't make an x to the 5th out of this, so I'm not going to try. But I can replace this dx with something, so let's do that. Let's say then that du over 2x is equal to dx, and that gives us somewhere to go with this thing. So now I can make some substitutions. I can say that this is the integral. I haven't done anything with the x to the 5th, but I can rewrite this as the square root of u, and I can replace the dx with a du over 2x. And there are a lot of different ways that I could write this, right? I could put this all over 2x. So this could be rewritten as the integral of x to the 5th times the square root of u over 2x du, which is a good way to look at this because this shows me that I can simplify this expression by reducing this to an x to the 4th and canceling that x. And I also can see that I have a 1/2 that's a constant that I can now remove from this equation. So I'm going to rewrite this as 1/2 times the integral of x to the 4th times the square root of u du. So at this point, it's important that we realize that we really can't move forward until we've found a way to represent x to the 4th in terms of u. I don't want mixed variables down here. So I'm going to go back up to this original expression and find a way to express x. If I subtract 1 from both sides, then u minus 1 equals x squared, and then I could take the square root of both sides, so the square root of u minus 1 is equal to x. So by that logic, the square root of u minus 1 to the 4th would equal x to the 4th. And that's the thing that I need to replace right there. All right, so I can rewrite this now as 1/2 times the integral of the square root of u minus 1 to the 4th power times the square root of u. And there's probably a more elegant way of writing that. So let's find a better way to express this. If we think of u minus 1, or the square root of u minus 1 as u minus 1 to the 1/2 power, then another way to write this is the integral of u minus 1 squared. And just to explain where that came from there, I'm rewriting this as u minus 1 to the 1/2 to the 4th, and then I'm going to multiply those exponents there. All right, don't forget your du. That is an important component here. I'm going to expand that u minus 1. So 1/2 times the integral of u squared minus 2u plus 1 times the square root of u du. And this wouldn't be a bad time to distribute that square root of u into that trinomial there. Remember, the square root of u is u to the 1/2. So when I multiply u to the 1/2 by u, that's adding those two things. So I'm going to have u to the 5/2. So I have 1/2 times the integral of u to the 5/2 minus 2 times u to the 3/2 plus u to the 1/2, or the square root of u du. And now I can use my power rule. So I've turned this into a situation where this is able to be anti-derived, anti-differentiated here pretty easily. So 1/2 times, all these exponents need to go up by an order of 1, and I'm going to need to compensate for those exponents as well. So this is going to have to be a u to the 7/2, but I need a 2/7 there, minus u to the 5/2, but I need a 2/5. And I already had a 2 there, right? Don't forget that 2 was already there. Plus a u to the 3/2, and I need a 2/3 to cancel that out, plus c. And now I'm just going to make this look a little bit nicer here. Okay, so I'm going to multiply the 1/2 by each of these terms. So I'm going to have a 1/7 u to the 7/2 minus 2/5 u to the 5/2. That 1/2 and that 2 cancel. Plus, I'm going to have a 1/3 u to the 3/2 plus some constant. Still doesn't really matter what that constant is. So the last thing I'm going to do is remember that at the beginning I substituted the square root of 1 plus x squared for u, so I have to replace that. So 1/7 times 1 plus x squared to the 7/2 minus 2/5 times 1 plus x squared to the 5/2 plus 1/3 times 1 plus x squared to the 3/2 plus c. So this is, so far, probably the most complicated example we've seen, and the concept that you want to take away from this is that you don't necessarily have to account for every single component of the original function when you make a u-substitution. It's just that if you've left something out, so in this case I'm just going to highlight the pieces that we accounted for when we made our u-substitution. We were able to take care of the 1 plus x squared, right? So we got that done. Okay, we were able to take care of the dx. All right, we got that done. But there was a component here that we weren't able to account for. And so what we did is we were able to just go back to that substitution we made with u and find out a way to express that component in terms of u. And that's a thing that we'll need to do moving forward. All right, one more example. This might not seem on the surface like a complicated example, but I don't know of a function whose derivative is tangent. So what we're going to first do is rewrite tangent using its definition. And so I'm going to express this as the integral of sine of x. And I have to rewrite this, sine of x over cosine of x dx. And when we do that, it becomes a little bit clearer that we do have a composition of two functions, right? There's some division going on here. So we have to be strategic about which of these two things we choose to be u. Because if I think of this as a composition of two functions, the way that I want to view this is sine of x times 1 over cosine of x. And so the composition is happening here. It's 1 over something, and that something is its own function. So when I make my substitution, I want to let u equal cosine of x. And that's going to mean that du is equal to negative sine of x dx. And most of that is pretty easy to deal with here. All right, so I'm only going to be replacing the sine and the dx with these components, so probably a nicer way to view this would be negative du, because these are the two components that I'm replacing in the original function. So now I can go ahead and make my substitution, and I'm going to say that instead of writing it that way, the original way, I'm going to rewrite this as negative 1 over u du. And I've skipped ahead a couple steps there, but I've made the substitution, and I've moved that constant negative 1 outside of the integral. And so now I can anti-differentiate that 1 over u du. So I have negative ln of u plus c. And so that's going to leave me with negative ln of u minus or plus c. Remember, it doesn't matter what that constant is. So lastly, I just need to make sure that I replace u with cosine of x, because that was the original substitution.